Let's do an example. Let's go back to our x cubed minus 7x plus 2, our first cubic. The derivative is 3x squared minus 7. And so the formula that we're going to use to continually calculate closer approximations is x sub n minus, this is the value of the function, x sub n cubed minus 7x sub n plus 2. That's the value of the function at x sub n. And then this is the value of the derivative at x sub n, 3x sub n squared minus 7. And so we plug that into the formula, and that's what we get for the iteration. So what does it do? What happens in this case? Well, let's look at what happens if we start at an x sub 0 of 0. So we just put in 0. If you do that and you use this iteration formula, you're going to get 0.2857 as your x sub 1. Your x sub 2 will be 0.2892, and then x sub 3, x sub 4, x sub 5, up to 4 decimal places, you don't get any change in the value. And that's because you're very close to the root, so the numerator in this quotient that's subtracted is a very tiny number. It's very close to 0. If it ever was 0, if you did actually hit the root, then your x's wouldn't change anymore. If we start at 5, the first iteration is 3.6471, and then we get 2.88, and we get these other values. And if we start at minus 2, we go to minus 3.6 and then minus 2.9. So we went from minus 2 to minus 3.6, and then we came back again towards the root at 2.7785, minus 2.7785. On this graph, I've labeled with the colors the green root, the blue root, and the red root, and we've seen how we've got iterations. And so we can calculate with Newton's method, we can calculate a lot of decimal places for each of those roots, and we could just keep iterating. I'll do one more example just quickly here. Suppose we take the equation y equals x cubed minus 7, and we ask for the root. So that's going to be the cube root of 7. We're trying to approximate, find a value for the cube root of 7. Y is x cubed minus 7. Y prime is minus 3x squared. The function that we iterate will be that xn plus 1 is x sub n minus x sub n cubed minus 7. That's the function, divided by 3 x sub n squared. And that is the function that we're going to iterate. We're going to make a first x sub 0 guess, and then we're using that we'll get x sub 1. Using that we'll get x sub 2, and as we keep going, we hope to get closer and closer to the cube root of 7. What I've actually done here is a different kind of notation that you may run into. On the right-hand side, we can take a common denominator. We can write this as 3x sub n cubed over 3x sub n squared. And then we can take the common denominator, and we get this quotient, 2x cubed plus 7 over 3x squared, and we take that and we plug it into x. So this is a notation that means x is replaced with the value on the right, and that becomes the iteration that you do. So this is just a different way of expressing that iteration. And if you do that, we're going to start at 2, and we get this kind of on a convergence. We see that almost immediately we get many decimal places, and they don't change anymore. We have converged quite quickly to the cube root of 7. And so before going on, we should say something about Newton's method in general. It doesn't actually always work. Sometimes it doesn't even work at all. It just goes haywire. But for most functions, it does work very well. The basic questions are: how do we pick a starting point? How many iterations should we use? How can we tell when the method is working and when it's not working? And what kinds of things can go wrong? Well, in the following examples, I'm going to show a few of the things that can go wrong, and then we'll say something when we're wrapping up about how you can answer all of these questions.